Hi everybody. So we're going to do a bit more Sudoku today in Differential Dataflow. Now we've done a few of these videos before, two of them before, and those might be a good place to start to catch up on what we're up to. I'll try to do a little brief refresher though. So we're trying to solve Sudoku problems using Differential Dataflow. Sudoku is this problem where you have a 9 by 9 grid and you're supposed to put the numbers 1 through 9 in each of these locations, each exactly 9 times. There are these three constraints that in each row a number should appear exactly once. Each column, each number should appear exactly once. And in each sort of obvious 3 by 3 region, of which there are 9, each number should appear exactly once. These constraints, combined with some initial conditions, so initial assignments of values to particular row and column locations, drives some inference about what are the possible values we might find in various locations. And we wrote one of those previously and then tidied it up a little bit. So there are at least two rules that you can use. We did the first one here, which is that if there's a specific value in one location, so the only possibility for there is this one value, that rules out that value from the same row, other locations in the same row, the same column, and the same 3 by 3 cell. And you can apply that rule, run it forward, and it turns out for the problem that we were looking at, that was actually good enough. So we amped things up a little bit and we started removing hints. What we're going to do today is we're going to apply a different rule. This is the sort of second rule that we could use, which says that if you have a row, a column, or a cell, that and there's only one location in it that has a particular value, oh, that's got to be set. That needs to be the one. So if there's a row and a lot of people have a lot of different values, but only one person has a 4, that person has to be the 4. So that's a different sort of constraint. We're going to implement this rule, and we're going to sort of add it to our big pile of rules, and we're going to see if we can get any lift out of this additional rule. If you might remember from previous things what we did to run the computation. Let's clear this out over here and show you. So when we run the computation, we're actually going to load up this puzzle over here, but then we're going to start erasing characters from it. So we're going to load it up, we're going to run our inference, we're going to find that we got all the correct answers. You should see up at the top. So we're going to be reporting these counts. How many distinct values are there in each location, counted up across locations. So all 81 locations have just one possible value. It means we solve the problem. Then we start removing things. We remove the 5, and you notice here that between round 0 and 1, nothing changed. That's great. That means we remove the 5. We were still able to do the full inference and figure out all the values. Things start to get a little worse. Some of the locations that only had one value, 6 of them in particular, locations that only had one value now have 2 values. That's annoying. Around 5, something catastrophic happens. I'm not really sure what, but this is when we remove the 7. And a whole bunch of those uniquely determined locations vanish and become blurry smears. And things just sort of get worse. And by the end of everything, at the very end, we've erased all of the characters. And of course, there should, at that point, be in total 81 locations that have 9s in them. So what we're going to do is we're gonna capture this data. I'm gonna stash it in a little buffer over here, and what we're gonna do is write some new rules, try to rerun this, and see if things don't fall apart quite so much. Maybe this won't fall apart here. We won't have this initial smear. Maybe we won't have this blurry disaster and collapse. We still expect at the very end of the day to have absolutely nothing determined. When there's no input, there's really nothing we can do, but perhaps we can be a little tighter along the way with the amount of uncertainty in our game board. All right, so I've sort of sketched, I guess, what the main program here does. This is mostly just calling off to building up a board. I guess I should say the board is a collection of triples of val, comma row, comma col, meaning the value val could possibly exist in this row and this column. Nothing prevents that. and it's going to be the initial conditions which tell us, well, some locations have only one possibility, others have 9, and our rules that are going to develop and reduce those possibilities. Yeah, and then we print these outputs here that break down the number of cells with the various distinct values, and we start popping out the values that exist and putting in the unknown character. And that's sort of the little harness we've got to run our computation. Where most of our thinking occurs, let's tidy this up for us, most of our thinking occurs down in this method that I've just called Sudoku. That takes in some initial starting configuration. It's a collection of these triples, and its job is to produce as output a new collection of these triples, hopefully reduced. We've hopefully thrown away a bunch of these possibilities, these candidates that we've decided are no longer actually reasonable. And the rough idea is to repeatedly apply some iterative rule. And we had an iterative rule before that said, this is sort of this forward propagation thing that says, if a location is determined, meaning if there's exactly one thing at that location, yeah, then we should take that information, go look up that information, figure out what value it actually is, and tell everyone else in that same row, in that same column, and in that same grid cell that they're not welcome. We got to get rid of that candidate. And that's what we do down here, essentially, is put together all these exclusions and delete them from a set of candidates and repeat. So that's roughly the algorithm. I'm going to make a mental note here, by the way. Oops. Mental note, if I can find the right... there we go. I've totally just blown away a whole bunch of... there we go. Mental note here that we're going to want to fix this up. I have to be totally candid with you. I played around a little bit with this beforehand and got myself really confused. And it turns out there's a subtle bug related to this line if we are careless as we continue. And I'm just going to call this out now so that I don't forget later on. All right, but what does the world look like? We've gotten ourselves to this point where we have what we were just going to return as the next iteration. Let's just call it something new. Candidates equals, and we're going to put a semicolon at the end. Semicolons are very important. And the gist here is that we're going to continue actually on from this point. Instead of just returning this and saying, go for it again, we are going to do some new rules. So what's a good sort of new rule to write down? So we're going to be looking at questions like, for any particular row, maybe in value, is there exactly one representative of that row value pair across all columns, I guess? And if so, we're going to excitedly pick out that row column value triple and insist that you are now that. You're not anything else. And yeah, so let's we can totally start to write stuff like that. So let's see, let row val be, we're gonna take the candidates, we're gonna hit them with a map to take the val row call triple and turn it into a we're just gonna take the val in the row, I guess, out. I think the plan, sort of like up above, is we're gonna just drop the call on the floor for the moment and say if this thing has, so we're actually going to steal some logic from that we used previously, this stuff right here. If a little reformatting to if this has, and we're going to need to obviously rename this to something a little bit better, val row, if this count is exactly 1, meaning like there's only one contributing column in this row of this value, then, well, that's terrifying. We should flag this as a very important row and val to preserve. Otherwise, let it be 0. So if this has 3 representatives, then don't care, right? It's not going to be part of this set. And we are going to we're going to lock in some values based on, actually, let's well, we can do this here too, actually. We're going to lock in some some values here. So we're going to take the candidates. Let's call this like a row lock, I guess. Is going to be the candidates, and we're going to do a little semi-join like we did up above. We did a little semi-join here. We're going to do a very similar thing here. Candidates, we're going to need to shift them around a little bit to get them into an appropriate val, row, call. Turn that into, what do we have? Val, row, call. Semi-join with these row val folks. So the intent here is that we have discovered in this collection row val those, maybe I should have called it val row. Oh well. Those pairs of value and row that are in parallel, and we need to go track down the, we believe, single representative column from that. And let's do a little map afterwards, just to make this be back in the same form. So we had val row call. We'll put it back as a val row call. And the reason we do this is because we're going to do this for a few different things. These, like both the columns and the cells, and then we're going to want to put together this pile of sort of locked in values. And yeah. All right. So we do the same thing now for columns. I'm going to make a little mental note here of what's going on, by the way. Determine rows and values with a single representative. All right, we're going to do the same thing with columns. We're going to unindent everything. Sorry about that. So I'm going to call this call val. That's probably terrible, but... And we're going to put in val, call. And there, we're going to apply the same threshold. Right, the logic is still the same, independent of whether it's values or columns or whatever it is. We will want to move this around and make sure that when we do the semi-join, we're joining on val and column, and that row is just passed around as data. Absolutely want to make sure to semi-join with call val. And we're going to do the same little switch again. Here, to put these back in some common order, we'll give this a better name. Let's call it call lock. Yeah, good. And we'll give it a nice comment as well, just so that we know what's going on in the future. And for for those of you who have already muted me a long time ago, you can see what's going on with the text. Okay, so we could, these are reasonably clean. We're gonna need, as a sort of a final thing down here, to install, apply the lock to enforce single choices in locked locations. And that's unimplemented. Before we do that, we're going to need to write the cell version of this. And the cell version of this is unfortunately a little more complicated. So the way we're going to do that, we're going to steal some code up here. And I hope this is the right way to do it. It's all a little bit gross. But we're going to do let cell val. This is going to look very similar, but I've already copied and pasted the thing that I want. So dot map of val, row, call. Now we're going to need all of these folks because they all participate in this thing. So instead of just a row or just a column, we're going to have the pair of row off, call off val, which row off and call off uniquely determine the grid cell that we're in, and we're going to apply the same threshold to say, well, so it's fortunately differential data flow is nice and just lets you say you want a pair of a pair and a val. That's totally fine. That's a totally legitimate thing that you could throw into here. Wait, we should totally, in order to parallel all these previous things, we should put val first. Great. And this is going to be val of val cell. But this is exactly the same logic down here, just with a slightly weirder identifier. And now we're going to steal this same sort of thing as well, except we're going to, again, we're going to need to write a little bit more grotty logic. So we're doing a semi-join with a cell identifier and a val identifier. Sorry, I'm just mentally double checking to make sure I have all these things right. Yeah, I really should have called these things val underscore blah. It's a tragedy. Actually, we can totally fix this. There. And this is going to be val underscore cell down here. Sorry, that's like a catastrophe waiting to happen. Getting those backwards because they're all the same type, unfortunately, right? We haven't in a more rigorous world we would distinguish row and column as separate wrapped types so that we couldn't accidentally interpret one as the other. Yeah, we didn't do that though. So what are we doing here? We're not just going to slap some call in there. We're going to need to, unfortunately, we're going to need to go and compute. Yeah, we'll roughly be doing this stuff. So let's steal all of that. What we're going to do is we're going to take this as the key, and we'll just, for simplicity, keep the row and the call over here. So we've got a pair of things, something that looks like a nice key, and you can see that's exactly what we had up here with our threshold, and some data associated with it. We're going to semi-join it over here, and now we have some. Yeah, when we're done, we've kept the values and cells that were uniquely determined, as well as the row and column that they originated from. And we're just going to rehydrate, in a sense, this triple val roll call, and we'll just throw away this garbage weird thing there. So we need to comment this, obviously. Great. Now this is a lot wordier than what we had before, and I apologize for that. The concepts, though, I don't think are really all that crazy. So like, really, we've just done this thing 3 times, though unfortunately we had to shuffle around the data a few different times, and it's a slightly wordy way to put together something. Maybe there's more succinct ways to write this in other frameworks. All right, but we now have 3 things of interest to us: row lock, call lock, and cell lock, all of which are things that should, if seen, force a value to be a particular thing. So what's a good way to do that? So there are a few ways, right? Like, we could go and just delete, essentially we want to take the rows and columns that are present in a set and delete all candidates that have those rows and columns, and then install the locked values. Right, that's totally a thing we could do. Not at all opposed to that, actually. We might as well type that out. I was thinking we might actually do something else, but let's see what this looks like. So if we take candidates, and we I'm going to first actually form just some let locked equals, and we're going to do row lock dot concat call lock dot concat cell lock dot distinct. So I want to have distinct things here. I'm going to sort of assume for the moment, this is a little silly, that we don't have conflicting requirements. So I'm just going to imagine that there's, if this collection is distinct, then there's only one occurrence of row and call in this collection. You'll see why in just a moment. So we take our candidates, we're going to hit them with a map, because we always have to do that. Val, row, and call, and we're going to turn this into pair of row, comma, call, and val. And we're going to dot anti-join this with locked dot map. So locked is val row call, and all that we're really saying is we're not really worried about what the particular value is, but if you have a row and a column that are locked, you need to go away. So this is going to produce row call val things, which we can then shuffle around again. Row call val, put them back into val row call form. Then we can concat in the locked values and delete the unimplemented. And that's actually not so distasteful. I was going to do something a bit more clever, and you know how clever it can be. Actually, we should absolutely, because we had this problem last time, right? Anti-join has a path through it. We'll probably be fine. Anti-join has a path through it that does not consolidate the data, and that can... You want to make sure that all of your paths through your data flow and differential data flow have at least one operator that will take a breath, and if things add up to 0, so if there are various canceling updates, actually ensure that nothing is produced as output. No data continue to flow around the data flow. I was going to write something a bit more clever that roughly tracked what we did up here with these exclusions. You might remember we just slammed them all together. So we could slam together all of our lockings in with the actual candidates. And here we just said, keep the things that are exactly 1, which basically meant keep the things that didn't have any exclusions. We could do something similar where instead what we keep are the things that are exactly 2, right? Because we've just added in. Actually, I'm just going to steal that code and it's so gross. Anyhow, roughly we could do roughly the same thing there, and I think that got us like 5% performance bump last time. I forget exactly what. Let's see if this compiles. Actually, sorry. Cargo check is the right way to do this. So anti-join is already complaining. That's fine. That's super easy. So incorrect closed delimiter. We've got this is like classic anti-join. So I deleted the parens, which I totally shouldn't have done. Oh yeah, we who's in charge of this show? We actually have to complete our map expression before anyone should be expected to. Cannot find rows off. That's right. There's no rows off. That's no. Okay. Yeah. Okay, computer. Cannot find val cell. Cell. Oh, did we not? We didn't switch that around either. This was absolutely one of the things we should switch around to make sure that it lines up with the order of the variables in it. Rows off. Yes, that's still not a thing. And map here is map is always of one thing, even if it's a triple. All right. Let's see. So that's compiled. That usually in Rust that means it's correct. So let's just run it and see what happens. I do happen to know that there's a bug that we're going to fix. This thing right here, and I might even try to explain why it's a bug. It's a bit subtle, and I went kind of deep in there to figure out what the world was going on. So we saved previously some output here. Let's go and look around and see how much. Where did I save it from? Cargo run. No, we're just gonna. Sorry, I want this to line up. This is just a little anal retentive, but soup. Steal everything. Go over here. Ba-bam. So, are these different? So this is the unmodified, like what we started with at the beginning of the session. And if we flip over here quickly, yes, they're different. So first of all, the running times are different. that's absolutely correct. They're slower now. But also, like, this 32 is different. So it's not a major difference. It means that, we were able to resolve 8 more locations uniquely at this point. There's going to be a cascade of changes going down just because the changes here probably, the 8 that we saved probably become confused a little earlier. Like right here, for example, in round 10, we just lose 1 bit of uniquely defined thing. And well, I guess in round 10 over here, nothing actually changes. That's pretty cool. Round 13 is where we drop off with a bunch more. Round 13. So by round 13, we've lost 2. And that sort of gets made up for by this loss of 5 against the 8 we saved. Anyhow, you can interpret this at your discretion. So yeah, it definitely did something. That's pretty exciting. Now, it did do something, but also it's buggy. It's buggy, as far as I can tell, not in like a correctness affecting way, just in a completeness affecting way. So if we look at our exciting data flow here, we're not going to be able to look at the whole thing, but I'm going to talk you through the defect that I hit my head against for a little while. We've written an iterative computation that starts from some collection and iterates, sort of comes back with this inner collection and says, hey, why don't you do some stuff with me? And you might remember from last episode when we were tidying up, I asserted that it's like super smart for this computation to not concatenate in the current set of candidates, but actually just go back to the original ones that we started with. Because what we're doing is repeatedly locking down locations, and as that set of lockdown locations grows, well, there's no particular reason to use the current set of candidates. If a location is locked down, it's whatever. If it's uniquely determined, right, it's just whatever it was in the original collection. So what that means, though, unfortunately, is this candidates thing is going to reflect only whatever we can learn about determined locations and the starting collection. So if we make other minor steps, minor restrictions to the set of candidates, for example, by crossing out certain locations, that is not going to be reflected. The information is going to get lost, basically. We're going to maybe make a little bit of minor progress in the background and say like, ooh, we've restricted some of the things off of inner, and by the time we get down here, we're going to say, well, if it didn't show up as a determined location, we don't care. So what we're going to do is we're going to fix this up by just going back to have a little performance regression here, but that's fine because you'll see. We're just going to do that. So we're going to say that the candidates that we propagate down through the rest of the computation are not just the initial state minus any exclusions, but are actually the whatever we had been working on minus any exclusions, which allows us to keep any progress that we made. So we're going to do another run here now, and hopefully I haven't actually seen the results of this, so but I'm aware of the fact that there's a bit of discrepancy and in a way that causes me a lot of pain. So great. Let's take all of this, put it in a new buffer over here, and now we can potentially see these buffers are not in the right order, annoyingly. So this is the original thing that we did from at the beginning of the session where we started from. It's got a minus 40 here in round 5. We improved that a little bit to this minus 32 in round 5, and then like quiet time down to round 13. In contrast with 40 and then some noise at 10 and down to 13. Now, if we look at what we actually got to with this new rule here, it's actually quiet at round 5, quiet at round 10, some noise in 13, but not nearly as much as in the others. So like the first, this has stayed the same, of course, these ambiguities here. But if we look at the first time we lose some specific values, it's 31 there, which is already better than the 32 we lost up here, and certainly better than the 32 and additional 5 down there. So it's like 37 we could have lost. This it was like 42 or something like that. It's a -1, a -1, a -40. So just losing 31 is already pretty solid, and I wouldn't be surprised if we find that these other terms here. So let's take a peek and see if we lose 5. 5 is the most chaotic we get by round 13. In our original run, already at round 5 we were had 5s and 6s. And over here we had a 5 already around 5, and at 13 we've got a 6 and some more 5s. So yeah, this new rule, or class of rules, I guess. Sorry, this second half of the inference is it's relatively effective. It does some good stuff, particularly if we had to start guessing, and that's the thing that we're sort of working towards. If we had to start guessing at any of these points to try to find the right solution, we've done a reasonably decent job of restricting down the space of things we have to guess. So, in some world, obviously not how things are actually going to play out, but like if we actually had to guess for all of the places that used to be well determined, 31 locations that we used to know, and now there's at least 2 values. 2 to the 31 is a large number. That's not actually how much work we're going to have to do, but you can sort of see how thinning down all of these possible values cuts the search space down a lot for the moment where we have to get a bit more brute force. But yeah, actually, before we go, I'll do like a release build, and we can see. This is the sort of thing that took like between 42 and 45 milliseconds last time. We've added a lot of data flow here though, so like we're doing more work to get a more precise answer. That's good. Potentially, like there's a world in which it goes faster. It probably won't. There's a world in which it goes faster because it converges faster. Right? Like the amount of work we do in differential data flow is sort of dependent on how much is changing in the computation, and the faster you can actually get yourself to a this is like a lot slower, right? Just rerun that to make sure. But so this used to be half this basically, and that's maybe not too surprising because we've added what feels like, to be totally honest, more than twice as much computation as we had before. But so it is. We've computed. Oh, this is sort of nice. This is it's on average, just a little bit over a millisecond per configuration that we're looking at. It's sort of cute. Some of these go really quite fast because there's really not very much changing. And the main thing, just to call it out again, the main thing that one needs to be a little bit careful about is listening to people like me make flip comments about how easy it is to do optimizations, like swapping out your iterative collection for some cutesy constant outer collection. If you actually leave that in, basically you just don't make as much progress as you could. You don't actually reach the conclusion of the application of this rule. So so I think that's probably as far as we're going to go today. There's another cute thing to do before we start going into the guessing parts. There's a neat rule. It's the same, basically generalization of the same rule, where instead of just saying, I'm sure you've used this if you've played Sudoku, but instead of just saying like if there's a value in a row where this is the only occurrence of the value in the row, we could totally take for each row the collection of all values and their counts, and observe, for example, if there's 2 occurrences of a 7 and 2 occurrences of a 4, both in the same places. We don't know who's a 4 and who's a 7, but we know that they aren't anything else. Right? So you find these often in Sudoku, you find these pairs that where you're like, well, it's got to be, I don't know, there's some symmetry here. I don't know who's the 4, who's the 7, but everything else is right out. I'll just delete all of those possibilities. And that has the potential. Typically what that does is that unlocks, there's some other dimension that you're looking in that's like, oh, well, it can't be a 6 anymore. So I guess, and you solve a little bit that way. We will probably try to put that rule in place and see if that gets us anything. Though to be totally honest, we're like in a fairly weird space right now, right? Where we've deleted enough of the hints that it's not even clear that we're in a uniquely down here in a uniquely defined solution anymore, that guessing or sophisticated additional rules would even lead us to a solution. But I'm going to stop there, and I'm going to let all of you all get excited about what's coming next.